Hi everyone. In this video I would like to discuss about knocking off IC engine. Knocking off an internal combustion engine, it is the metallic sound, rattling noise produced in an IC engine when fuel and air mixture undergoes uneven combustion. This is because of the random movement of the piston that is within the cylinder. Before going to discuss the reasons for knocking, let us discuss briefly the four strokes of this IC engine. This has four strokes: suction stroke, compression stroke, power stroke, and exhaust stroke. Okay. In the first stroke, we have inlet which is kept open, that is for fuel and air mixture. Okay, and the exhaust valve is closed. This is the exhaust valve and this is the inlet valve, and this is the spark plug which is to produce the spark, and this is the cylinder where you fill fuel and air mixture, and this is the piston which can go up and down during different strokes, and then this is connected to this piston. When it starts moving up and down, then this starts rotating, then the further the vehicles or wheels starts moving. This is a crankshaft. During intake stroke, inlet is open, outlet is closed, and then in the first stroke the fuel and air mixture is admitted, then the piston moves down to maximum. This is the volume of fuel and air mixture at the end of suction stroke. We take it as V1. V1 is at the end of suction stroke. Once you fill the maximum amount of fuel and air inside the cylinder, then this piston is compressed. It is moving up. During this stroke, both the valves are closed. Inlet and outlet are closed. This fuel and air mixture is compressed to the maximum volume. As a result of that, the temperature inside also increases because of high pressure. Okay. Then in the next stroke, that is called power stroke, spark is produced here. When the spark is produced, the compressed fuel and air mixture catches fire and undergoes combustion. As a result, a flame front, we get a flame front, this is called flame front, is produced, and this flame front produces a large volume of pressure because of combustion and pushes the piston down. If this piston moves down uniformly, then there is no knocking. During this stroke, both the valves are also closed. Next, in the last stroke, once the fuel undergoes complete combustion, then the piston is again pushed back. As a result, all these burned gases, carbon dioxide and other gases, it is let out through this exhaust. During this stroke, this outlet is kept open, and so all the burned gases are escaped out through this exit. During this, inlet is closed and outlet is open. During the second compression stroke and power stroke, both the valves, both inlet and exhaust, are closed. In the first stroke, inlet is open, the exhaust is closed. In the next two strokes, that is compression and power stroke, both inlet and exhaust are closed. And in the last stroke, that is exhaust stroke, okay, the exhaust is open, inlet is closed. This is how the internal combustion engine works. If engine has to run smoothly without making any knocking or sound, this piston has to move uniformly. Okay. If it moves randomly or unevenly, then only the knocking in the internal combustion engine. The reasons for knocking, this non-uniform movement of the piston, is because of uneven combustion of fuel and air mixture. Let us look at the main three reasons for this knocking. The first reason for knocking is pre-ignition. Pre-ignition is ignition before the spark from the spark plug. Okay. So before the third stroke, in the second stroke when we are compressing the fuel, okay, if you compress beyond certain value, then whatever the pressure which is created inside, that also increases the temperature, very high temperature, and that temperature is enough for the fuel and air mixture to catch the fire and undergoes combustion. This happens before the spark, before the power stroke. This happens. This is because of high compression ratio. Compression ratio is the ratio of the fuel and air mixture at the end of the first stroke. That means when you fill fuel and air, we get some volume, maximum volume, this volume. Then in the second stroke, we compress the piston. Okay, we compress the piston to some value, that is V2. So V1 by V2 is always greater than 1. Since V1 is greater always, V2 is when you are compressing, V2 is decreasing. So therefore V1 by V2 is always greater than 1. And if CR value increases, means you are decreasing the volume V2. Means we are compressing that volume to maximum. So if CR value increases, means the pressure inside you are compressing to the maximum. As a result, the pressure also increases and then temperature also increases. So if that CR value crosses the specified value for a given combustion engine, IC engine, then pre-ignition takes place. Higher the CR value, higher is the pressure as well as temperature. If CR value crosses beyond certain value, temperature increases and the fuel and air, F and A means fuel and air mixture, ignites before the spark from the spark plug. This causes uneven or sudden combustion that results in knocking. I will discuss the graph variation later. Next, let us look at the second reason for knocking. This is self-ignition. Self-ignition means some part of the fuel, the last portion of the fuel, which ignites without the flame. Okay, this is at the end of power stroke. When the power stroke is about to complete, means when the fuel here the spark is produced, the flame front is moving down. In the last portion, when is about to burn, because of insufficient oxygen, there will be a formation of some peroxides. Instead of forming peroxides, because of insufficient fuel and air ratio, there is a chance of formation of peroxides. If peroxides are formed, which catalyzes the formation of highly reactive free radicals. We know that free radicals are highly reactive. That results in sudden explosive combustion from the bottom of the combustion chamber. This results in the two types of flame. Flame front from the flame spark that is coming down, and the last portion of the fuel. You cannot expect sometimes the fuel catches from the bottom. That is because of peroxides and free radicals formation. And piston is not getting the pressure uniformly. This results in random movement of the piston and results in knocking. So these are some of the reactions showing the formation of peroxides. Okay, and this picture, this graph indicates this is if compression ratio increases, the power output also increases. You should not cross beyond certain CR value. If you cross certain value, because of knocking, the power output decreases. Okay. Highest HUCU means this is highest useful compression ratio. This is fixed for a given bomb calorimeter. You should not cross beyond this. Up to this peak, that engine will give you more power output. If it is beyond this, then it leads to pre-ignition and knocking, and you won't get the power output decreases. And this is a picture showing the self-ignition. Look at this, spark is produced here and the flame front should move like this. This is the primary flame front that we are creating by producing the spark. Because of insufficient fuel and air ratio, you can also expect some spark, self-ignition, which takes place at the bottom of the fuel. This results in uneven combustion inside the combustion chamber, and that pushes the piston randomly. That results in knocking. This is the secondary unwanted flame front which is created. This is the secondary unwanted flame front which is created because of improper fuel and air ratio. This is due to self-ignition. Okay. As I told you, the self-ignition is because of the formation of peroxides and all. And peroxides results in the formation of free radicals. We know that if free radicals are stable, then there is no explosive combustion and less knocking. If the free radicals are highly reactive, then highly explosive combustion, more knocking. We know that if the petrol sample is having a hydrocarbon chain, which can form a primary free radicals. We know that primary free radicals are highly unstable, means highly reactive. They undergo explosive combustion. So, however, if the free radicals are branched, are in the form of aromatics, then they are more stable actually because of delocalization in case of aromatics and in case of alkene. And in case of tertiary and secondary free radicals, they are more stable as compared to primary. So therefore, if the petrol sample can produce secondary or tertiary or branched free radicals or aromatic free radicals, they are less explosive, less knocking. So therefore, this the knocking also depends on the chemical structure. The tendency to knock has been found to decrease in this adder. N-alkane, because they are straight chain, they can form primary free radicals. Primary free radicals are highly reactive and they can undergo highly explosive combustion. So therefore, the petrol sample is having more straight chain hydrocarbons, then it is having more knocking. Then substituted, they are less. They can produce slightly more stable free radicals, therefore less knocking. Then cycloalkane, alkenes, more polysubstituted means that it may result in tertiary free radicals. Hence, it is more stable, less knocking. Aromatic compounds, again, because of delocalization and resonance, the free radical formed in aromatic compounds are more stable, therefore the less knocking. Okay, it does not mean that if you can fill petrol with more aromatic compounds, it will definitely not produce any sound, or it has less knocking. However, we should also see the calorific value of the chemical fuel, not only knocking. If you can fill only benzene or toluene, the calorific value considerably, it will come down. So therefore, we should see all the characteristics, even including knocking and calorific value and all the other important characteristics of the fuel. Here we are talking about only the knocking part. Okay. So knocking is a metallic sound which produces in an IC engine due to uneven combustion of fuel and air mixture. This is because of three reasons. Okay, pre-ignition because of if CR value crosses certain specified value, suddenly the fuel and air mixture catches the fire before the spark produced from the spark plug. That is one reason. Second reason is self-ignition. Self-ignition, if there is an improper fuel and air ratio, there is a formation of peroxides. When the last portion of the fuel is about to burn, there is another secondary flame front is created that produces peroxides and free radicals. Free radicals undergo explosive combustion from the bottom, and that again results in uneven combustion and rattling noise is produced. This all depends on the chemical structure. Straight chain hydrocarbons are more knocking than branched chain, than tertiary polysubstituted, than alkenes, than aromatic compounds. Okay. Let us look at the effects of knocking. If knocking increases, it reduces power output. It leads to mechanical damage to the engine because of random movement of the piston. It overheats the engine. Noise pollution decreases the energy efficiency. So how to reduce knocking? So by maintaining optimum CR value, so that we can prevent the pre-ignition, or if you can maintain the proper fuel and air ratio, you can prevent self-ignition. Or if you can modify the structure of the hydrocarbon, straight chain to branched, branched to cyclic, cyclic to aromatic, you can modify, you can create the stable free radicals inside so that you can reduce the knocking. I hope this video is useful to all the guys who are studying engineering chemistry. If you feel this video is useful to your friends, please like it, comment it, share it, and please subscribe. Thank you very much.